You ever pull out your phone and it just instantly finds all the faces in a picture? Or you see a video of a self-driving car navigating a street? It really does feel like magic. Well, today, we're going to pull back the curtain and see exactly how that magic works, how an AI actually learns to see.
Okay, so let's just dive right in. To you and me, the image on the left is a cat. Obvious, right? But to a computer, it sees the thing on the right, just a massive grid of numbers. Every single pixel in that photo is just a number that tells the computer how bright and what color it is. That's all it gets.
And you know, this massive disconnect is the fundamental challenge, the core problem of all computer vision. The machine doesn't see a cat, it sees a spreadsheet of raw data. So the real question is, how on earth do we teach it to get from that jumble of numbers to the idea of a cat?
Well, this problem actually has a name. It's called the semantic gap. It's this huge canyon between our rich, meaningful understanding of an image, that's a fluffy cat sitting on a rug, and the computer's cold, hard data. Our entire goal here is to build a bridge across that gap.
And just think about how basic this data is. For a typical color image, each pixel is just 3 numbers, one for red, one for green, and one for blue, each from 0 to 255. That's literally it. There's no built-in concept of fur or whiskers or pointy ears, just numbers.
And to make things even crazier, look at this. These are all cats, right? But from a pure pixel-by-pixel point of view, they are completely different. You've got different breeds, colors, poses. Some are sleeping, some are running. The pixels are all over the place. This is called intra-class variation, and it's exactly why you can't just write a simple program with rules like, if pixels are orange and pointy, it's a cat. It would never work.
So if we can't write the rules by hand, what do? Well, we flip the entire strategy on its head. We use what's called a data-driven approach. Instead of trying to explain what a cat is, we just show the computer thousands and thousands of pictures of cats and say, you figure it out.
This quote really hits the nail on the head. Recognizing something like a cat isn't a neat, logical problem like sorting numbers, where you can write a perfect step-by-step program. It's messy, it's intuitive, and it needs a totally different way of thinking.
So this whole data-driven thing usually follows a simple 3-step recipe. First, you gather your ingredients, a huge collection of images that humans have already labeled: cat, dog, car, whatever. Second, you use that data to train a machine learning model, which is called a classifier. You're basically letting it study the examples. And finally, the big test. You show it brand new images it's never seen before to see if it actually learned the concept.
For our explainer today, the AI is going to be studying from a famous textbook called the CIFAR-10 dataset. You can think of it like a giant stack of digital flashcards. It's got thousands of little pictures, all neatly labeled in 10 different categories, everything from airplanes and birds to dogs and trucks. This is the stuff our AI is going to learn from.
And when I say thousands, I really mean it. This CIFAR-10 training set has 50,000 images. That is a lot of homework. The AI is going to look at every single one of those pictures to start building an idea of what makes a car, and not a truck.
So what's the AI actually doing as it looks at all 50,000 of these images? Well, its first simplest strategy is to try and create what we can call a pixel template for each category.
We're going to start with a really basic AI model called a linear classifier. Here's the idea. After looking at, say, 5,000 pictures of cars, it tries to create a single average car by essentially mushing all those images together. It creates one ideal template for a car, one for a dog, one for a ship, and so on.
Then, when it sees a new, unknown picture, it basically holds it up against each of its 10 blurry, ghostly templates and asks, which one does this look the most like? It's a matching game. But this raises a really fascinating question. What do these learned templates actually look like?
All right, this is the part I love. We can actually peek inside the AI's brain, so to speak, and visualize these templates. We can literally see what the AI has learned to see.
So, the moment of truth. After sifting through 50,000 images, what is the AI's final, averaged-out mental picture of a frog, or an airplane, or a horse? Let's take a look.
And here they are. How cool is that? Each one of these blurry squares is the AI's learned template for one of the 10 categories. You are literally looking at the AI's memory of what these objects look like based entirely on the data we gave it.
Now, I know they're fuzzy, but if you look closely, you can start to see what it's learned. The airplane template, top left, is kind of bluish. Why? Because most of the airplane pictures probably had a big blue sky in them. And look at the car right next to it. It's sort of a reddish blob in the middle, maybe because it saw a lot of red cars photographed from the front.
But okay, let's be honest. These are very blurry and very vague. This is just the first pass. The good news is we can do a lot better. We can make the AI's vision much, much clearer. Check this out. On the left, you've got those noisy first attempts we just saw. But on the right, that's what happens after we use some smarter training techniques. See how the templates are getting more defined? The car is starting to look way more like the front of a vehicle. And look at the horse, bottom right. You can almost make out the distinct two-headed shape it learned from seeing horses from the side.
So how do we get this kind of improvement? Well, it comes down to a few key tricks. We can give the AI more time to study, basically letting it review its flashcards over and over again. We can also give it a bigger brain, using a more complex network with more layers, so it can learn more detailed patterns. And we can use clever math tricks that help it ignore distracting background noise and focus on what's really important.
And that's really the big takeaway here. The quality of an AI's vision is a direct result of the quality of its training. More data, more time, and smarter algorithms are what turn a blurry, noisy guess into a much sharper, more accurate picture of the world.
And that kind of brings us to a final, pretty mind-blowing thought. We've just looked inside a very simple, beginner-level AI. It makes you wonder, what do the massive, incredibly powerful AI systems, the ones used in medicine, in security, on our social media feeds, what do they see? What hidden patterns have they learned to recognize about our world?